One final approximation we can make to make this equation even simpler is to look at the relative values of some of these numbers in here. Okay, so first thing we can do is look at our denominator. Our numerator. If we have K2 times our formal concentration, K2 is going to be a pretty small number in most cases. If that times the concentration is significantly larger than Kw, which is a really small number, then our numerator can be simplified, right? Because we can factor out the K1. Numerator will just be K1, K2, F. Basically, we can ignore this second term because Kw is a very, very small number. All right, so that's if this inequality is true, if K2F is much, much bigger than Kw, which is usually the case. While K2 is small, it's usually not so small as Kw. This term we can effectively ignore. And if K1 is much, much smaller than the formal concentration, then the denominator can be simplified. Becomes just K1, becomes just F, because K1 is small. We can take this second term, and this one will go away. Then our expression becomes, to give myself a little bit more space here, concentration of H plus is equal to the square root of K1, K2, F over F. Those F's just cancel, and we get it's the square root of K1, K2. So this is an even simpler version, and we can even make it one step simpler. If we take the negative log base 10 of both sides of the whole equation, we'll get pH on the left-hand side. That's the definition of pH. And then we'll get negative log base 10 of K1, K2 to the 1/2 power. I've written this in a little bit different notation here because if we have something raised to an exponent inside of a logarithm, the properties of logarithms are that we can take this exponent and multiply the logarithm by it, and it's equivalent. So we have negative 1/2. And we'll leave the negative with the log. 1/2 times negative log base 10 of K1 times K2. And one further property of logarithms is that if we have a logarithm of two things multiplied together, that is the same as the logarithm of each of those things added separately. So we can rewrite this again as 1/2 times negative log base 10 of K1 plus, or I should say minus log base 10 of K2, which these are now just the definitions of pKa, right? So pK1 and pK2. So we get 1/2 pK1 plus pK2. All right, and so this expression then becomes that the pH is just related to the pKa values, which is what we look up in a table anyway. So pH is equal to, 1/2, can't forget that, 1/2 of pKa1 plus pKa2. So it's just going to be the average. pH is basically the average of the two pKa values for our diprotic species. So if we use this with alanine, pH is 1/2 times 2.344 plus 9.868, which gives us 6.11. And from this much simplified equation, we get a result that's almost identical to that longer one that we used with the square root. So this is almost the same. And for many cases, if you just want a quick and easy calculation and you don't need to know the pH super accurately, this equation will get you most of the way. So this is a very handy equation for intermediate species of a diprotic species. So we are So we're done with this part. In the next video, we're looking as we get to the end of chapter 10. We're now going to move into buffers. We talked about buffers with monoprotic species. Now we're going to look at buffers with polyprotic species, specifically diprotic buffers, and then we'll extend it to polyprotic species.